Zsolt Regály, he is a visitor in our group. So I know Zsolt for, I don't know, 7-8 years since 2017, when I was working in Konkoly Observatory in Budapest. Basically, his specialty is on numerical simulations, focusing on star and planet formation, dust growth, and so on. So his early interests were modeling type 1 supernovae a very long time ago in 2001, when he got his master's. And then he went to industry, trying to do with battery technology, maximizing, optimizing stuff. But then he was not satisfied with industry, so he came back to science. In 2008, he joined Kies Dilemma, so that's in Germany, and then started working in physics again, and he got his PhD in 2012. Again, planet-disk interactions and so on. And after that, he was in Konkoly Observatory, and he was in a PI of computational astrophysics group till 2016. And after that, he is a PI of 3D NAL group, so numerical astrophysical lab, since 2016. And he's a very interesting person. In Budapest, he gives a public lecture or a series of lectures about exolife. So it's a series which are topics interested, which are relevant for exolife, exoplanets like AI and free will, some interesting topics. So if you talk with him, it's very interesting. And he has interests like cycling and astrophotography, opera, things like that. So yeah, very cool. And he's visiting our group with the funding. It's called Cost Action. So we applied for some funding, and for 2 weeks, the funding agency pays him to come here and do some research. So that's how he's visiting us. And I'm very excited to have Zsolt, so take it away.
Thank you for this nice, kind introduction. I'd like to speak about how dust inside disk affects of low mass planets. Basically, this is behind this title. And what we know is that planets are formed in these disks, which is a remnant material of star formation. And these planets are usually interact with some interesting phenomena. Okay, so here you can see 5 different stages of planet formation. First, we assume that disk is unperturbed or perturbed somehow, and these perturbations could be the seeds of planets or pebble. What we have to know first is that these protoplanetary disks are relatively low mass compared to the star, because we have about a one. The disk mass is canonically, I don't know, 1% mass of the star. So this disk contains mainly gas, which is again 1% of the total disk mass, and this gas is usually hydrogen, molecular hydrogen. So the 99% disk mass gas, and only 1% of the disk mass is solid material, which could be micrometer-sized dust, pebbles, or asteroids or planets. Okay. So planets interact with their disks and cause some perturbation in the gas. Here you can see a result of 3 numerical simulations which show the perturbation in gas caused by an Earth mass planet, 30 Earth mass planet, and 1 Jupiter mass planet. Usually we call these this region, I mean the 1 Earth mass, as the terrestrial planets. These are super Earths. Okay. What says the theory about the effect of this perturbation on the planet? Planets migrate, and I will show you how and why. So a long time ago, there was some theory to calculate the migration analytically. So basically, what we can say is that the A dot, so the change in the semi-major axis of the planet, is proportional to the gamma. Gamma is the torque exerted by the gas on the planet, and the impulse momentum of the planet divided by the impulse momentum of the planet. So the torque is practically a cross product of the distance of a given parcel of the disk and the planet with the gravitational force. So we can calculate this by this equation, but it cannot be, usually it cannot be solved analytically, just numerically. But these papers and many others between 2024 and 79, the analytic solution assume only first order perturbations and limited in 2 dimensions. These equations are valid only in 2 dimensions. So as a result, what we know is that the torque is proportional to the, for example, the planet square of the planet mass and several other parameters of the disk. I will maybe talk about this aspect ratios, small h, and the surface mass density of the disk. So basically the disk mass. Okay, the solution of these equations and these perturbations show us that planet migrates with this rate. The most important thing is that the migration is proportional to the planet mass. So which means that a larger planet migrates faster. And there is a function here which describes how fast is this migration and what is the sign of the migration. We have here a constant number. We see that the change in the semi-major axis is negative, which means that we have an inward migration usually. But due to these two other parameters of the surface mass density and the slope, which is V, and the slope of the temperature, this could be positive in a certain type of P and Q. But generally, the migration direction is inward. If we have a larger planet, we can see that not only spiral waves, but a gap is opened. And the torque, analytic torque solution says that the torque is proportional to the ratio of the surface, the original surface mass density at the orbit of the planet and the gap density. Generally, the migration is done inward as well, but it is inversely proportional to the planet mass, which means that a larger mass migrates slower. But again, we have a negative sign. So type 2 migration is almost in all cases directed inward. So what we know from the gas and the distribution of gas and the migrate inward in the type 1 regime. Planets, giant planets migrates inward again, but in a type 2 regime. I forget to mention that in type 2 regime, the viscosity is here, which means that this viscosity has a strong influence on the migration speed. Okay, but what about these 30 Earth mass planets? They are migrating extremely fast inward. And this is because of the fact that these planets are no longer in type 1 and not in the type 2 regime. And it cannot be seen, but they open an extremely weak gap. As a result, the migration is extremely strong for this planet mass. Okay. But what if we include what happens with the solid material in the gas, in the disk? Here you can see how small particles behave in the gaseous disk. But now in this plot, we're in the Cartesian geometry, but it's polar direction. What you can see, coupled gas looks like the very coupled dust. The distribution of very coupled dust look like the gas. Here you can see the gas. That the distribution I will determine like certain weights and we will the same pattern. We cannot do this slide, I showed that the disk is extremely thin. So the two-dimensional approximation differential. And the differential equation these two equations are is the particularly the due to the interaction of gas with dust, the gas orbits with a Keplerian, a subkeplerian velocity due to the gradient, pressure gradient. The solid usually moves. There is a velocity difference. A velocity difference means a headwind, and the headwind means black force. Black force affect the speed of dust particle, and the dust particle can back react to the gas. And there are some coupling equations between these differential equations. And the most important is the back force. Practically dependent on the size of the particle and the density ratio of the particle and the disk. I can ask a question about the sigma accretion. So the dust that's where you can disappear. It will be a logarithmic grid, which means that we have the star distribution of the big star, the hydrogen, and a logarithmic grid. Okay. Here today I will talk about the effect of the back force and the back direction and the effect of accretion. Planets usually accompany gas and dust. Small mass planets the gas accretion is due to the accretion of dust. The gas tries to go down now how I basically yes, this field eventually here, and the bar has a different rate. The piece of eta means that how fast is the accretion. And the simulation has been shown, the three different types of ether. 0.21 is the zero accretion in terms of material inside the sphere will be affected by the planet in a single orbit. But keep in mind that during this accretion, the material enters the space of the so about the literature, the first has a literature about the dust of pebbles was made by Pablo, then it was by and they basically in this picture they showed what is the torque exactly on the planet. Okay. Means that there's a positive torque and also Post number is it depends on the surface mass. Okay. So the colors means that we find we incorporate dust in the torque part. It means that the dust can reverse, even can reverse the migrate. Although the depth mass is only 1% of this time. Second paper, I published and I calculated what is the migrate the pebbles calculation. Distribution of the solid I do and the recent paper by Konkoly et al. Here, the model, the effect of dust on the planetary migration. But the people handle the dust as a pressureless fluid, rather particle. And in their simulations, the gas evolution is not, or the differential activity of gas is not coupled. They are just yes. Okay, so the last paper, my colleagues we investigated bacteria. What is the effect of accretion? So it's a flow that we have direction, accreting, and you can see the distribution of that couple the solid material here. Obviously, the planet accretes the solid material, then region. I think we increase or change the size of the dust number with the dust gas coupling dynamics different and because the accretion after more examples for the ledger Stokes number. What is the asymmetric distribution of solid material? Okay, we have a disk. Disk has could be distributed for material in rings. Every four represented by the mathematical from the possible that every so solid material is different than that. You can see that we have this kind of source profiles. Some value positive number although in the gas we have 100 times larger amount of mass. The source profile is actually compared to the solid material. What is the idea that offset? Just a toy model. I will show you the real torques which are, but this is just a toy model. What is the effect? So okay, why is this offset in real models? This is in this basically the spiral wave inside the planet and the spiral wave outside the planet little bit differs in density because the global density is increasing. It means that the inward spiral is a little bit stronger than the spiral, but the outward spiral distributed in a larger space. The complicate usual effect that the torque profile of gas is a little bit shifted down. But it can be shifted right. It depends on the details of the calculation. So this is just a toy model, how the torque profile looks like in a real simulation.
I think from the outside, the pebbles will accrete in that outer spiral, yeah, that will cause.
No, it is gas.
No, for the dust.
All the question was about the dust.
Shifted up to the red curve. So I think the pebbles will not down.
The planet move in this direction. But here we have that's material is solid material. But here we have the solid material behind the planet. We have actually what we were here. And if we calculate the torque of the region, the result will be something like this. Not for all those numbers. So just an example, how can we reverse the torque sign? So that's all. So if we include this, we will have a positive total torque, which means outward migration, which is different than what we analytical prediction is. We just think here. So it shows the work profiles mass planet, black is the gas profile, gas torque profile, and the red are the well coupled solid torque profile, or see different migration accretion efficiency. You can see the distribution of solid profiles differs for different systems. What is the effect of this? Picture it shows several models. Horizontal axis we have 0.1 Earth mass planet, 3, 3, and 10. The vertical axis includes the total torque normalized by gas. There will be no solid torque, it will be small, and everything will be so, no, -1 means an inward migration, but everything will be, if we include the solid, especially the accretion, you can see that sometimes the torque, the red region, this should be blue region, which means decreased amount of the migration is slowed down. However, in the green region, the torque values use a negative result. But you can see in amplitude, the variation is here. So we have a 1%. Solid content in the prototype is from here, but it can also change the now, you have the action. So we have the same function, therefore, but now we have the option of solid material into the gas. Why is complicated? Because the numerical handling for solid material, special solid, will be more complicated than that's why with the different in the same measure gas that here in the model normalized by non-vector. That is why that one that we size we have 3.3. These values, these models don't include any accretion. We have a 10% accretion and 3% accretion and what are the different colors and symbols. Okay, different colors mean the difference Stokes number. Here we have 0%, 10%, 100%. You usually see that you can change we have first, so masculine. Okay. If the back reaction, everything should be again at -1. Is that the back reaction, the gas or the back reaction is the same as the normal. But we can see that difference here. For example, again, in some cases, the direction, the gas the sign of the it means that the gas actually positive sometimes we can measure the positive gas score, especially this gas score, where the temperature special. So anyway, when you look at the thermal model, there are some models that the picture is the same. The total torque normalized by the therefore the back reaction model. We have seen this. Now we can see this back here. The vertical is the same, and we see that it's a huge effort. Then what we see, I think the effect we are seeing is I'm not loud. We don't better think something. This red are well coupled solid material, which is particularly efficiency, that we can see that the torque amplitude decreases, and even positive torque can be that's the number. The material which has fixed number of units. I think that it's twice as it migrates inward twice as faster than this gradual is the more solid material. Larger particles, and you see that it migrates outside. Actually, right. So we see locally isothermal the so-called ground dust, which accretion, which means that the migration is slowed down. Assume that the ratio of solid matter to the gas is only one. So basically, it's for a solar metal, it means that what if its metallicity is a bit higher? It could be 3 times higher, which means that we have 3 times more material than this. So the effect of solid accretion is multiplied by 3. The effect of back reaction is also multiplied by 3. It means that all these stored in the red vacuum need to be larger and positive. All stored in the green regime, -1, will be also strengthened in up amplitude, which would mean faster in the environment. The interesting thing is that happens in the regime between -0, because in this case, what we see is that the accretion the total torque, so decrease the speed of the migration. Certain amount of solid mass, which could turn the direction of migration, because with, I don't know, 3 times more solid mass, we would see that maybe these torques, because the effect that magnitude by the solid, and if we assume 3 times amount of solid, then it will be positive. So, first, the solid material plays an important role in the disk, especially in the planet disk interaction that for the migration of the planet. The effect of accretion is such that it increases the effect of solids. The back reaction of the solid material to the gas should be taken into account also. Otherwise, there are a couple of fast, small, transparent upward migration or slow downward migration. That's a couple of solid materials, pebbles, and because first inward or outward migration is different on the size. Metallicity of the disk and I have we found that migration of accreting. So it is not like depends. Are you up here? Can you go back to your equations? I wonder, I think when you want to have self-gravity, I am used that we need to solve the class equation. This is not yeah, so I was wondering about the polar, the stellar potential, the planetary. And we have I can go into the detail, but is this some kind of approximation or is this yes, this is no, this part this is the different in the polar coordinates because the here we have this which is required in the dimensional equation. One is that we have another in dimension and we want as close to 3 dimension as it's possible. And there are some experimental results for the parameter 6, then for 2D and 3D simulation. And another thing, the planet is in the middle of the south, then its potential is that important for the talks, or is this not really? I mean, the talks, are they provocation gradients or are they because of gravity? Because of gravity. Right. So that torques are. So that weight is very important for the talks, right? Yes. Yeah. No. My question would be: if this is an approximation. I will show you maybe with other very parameters very important. So, I will show you later more paper that I had an experiment and we found that all these phenomena decreases if we decrease the parameter. But what I noted here done in a form canonical. You see the big technique like this if we have some special handling that is the cell and the planet. If we allow the planet to migrate, then
maybe I need this in the beginning, but the solid material is contains within the body scale from dust up to pebble. When in reality, all these scales and material even the way how much is distributed over the scales of particular objects and the way how this objects are distributed over the piece would affect your drag force and your accretion rate.
Material distribution close to the outside for orbital distance, these are normalized torque, the normalization factor taking into account examination. But the migration rate would be different because the migration rate depends on the orbital distance.
And also on the distribution of your objects.
Therefore, the distribution
Combination of the right scale object closer to the star. That's you're further away.
this is why this is why you need long-term simulation. Migrate with regards to the size distribution, completely right, that we should incorporate several different Stokes numbers in one model.
But you emphasize that it's so important with backreacting.
Yes.
So the gas is also having a difference. You put all your mass into certain Stokes number. But in reality, you have a mixture of all these and also the gas.
Why would
Like
moves you will also continuously appear in the.
Even the constant Stokes number of the example.
Exactly.
Because if we assume a constant size distribution, then the Stokes number is not constant. However, usually the growth of solid material, the solid material grow unlikely to study. But this growth rate depends on the distance. The question is that how it called a constant Stokes number or even residual Stokes number. So yes, but it's the future. So as I mentioned, there are several papers cited our work, but up to this point, only 4 papers are dealing with numerical simulation, hydrodynamic simulation, like the solid torque. So that, which means that we have a lot to do.
you plan maybe to do that, so you have not only one size, one Stokes number.
First, I
number of them. First, several fluids.
Also hydrodynamic ability might be limited to count with like stable things.
exactly, right. So that's the issue. I will not explain more. For an Earth planet, and we see here predictive model for 10 times metallicity, the initial value. So this is the prediction that I'm if we ask you that so mass and but the so that would be an answer.
Yeah, good questions. Good question. The last one. So the efficiency parameter eta, which is very important from relations. Is there a way to measure it out observationally or with 3D simulations? How would you go about fixing it?
I think that we are usually even if it's hot due to accretion, surface area is small.
An observation.
So, at the moment. But what I'm certain is that the 100% accretion rate. But this is the largest one, but this model can have.
Okay, thanks to speaker.